So my name is Adam Haney. I'm the Chief Technology Officer of Bellhops, and we're a company based out of Chattanooga, Tennessee. So if you guys have met people that are from Chattanooga and you're like, why are all these Chattanooga people here? It's because we showed up in droves and you should all move there. And today I'm going to talk about digging into the abstract syntax tree module in Python because frankly, I didn't know it existed until a couple of months ago, and it's really horribly documented. And I thought it was really cool when I kind of stumbled across it, and I wanted to just kind of share what I had learned through a little adventure that I had through a code base. So basically the idea is, for this talk anyway, how can you write a Python program that takes a Python program as input? So if you've ever used something like pyflakes or the pep8 module or pylint or any of those things, I was really curious how they worked. And when I started diving into it, you quickly run into this sort of notion of abstract syntax trees and the way that those are evaluated and how Python takes code and turns it into something that's executable by the interpreter. So if anybody's ever used pyflakes before, basically the idea is it takes programs and it analyzes them for common mistakes. So it looks for things like variables that are defined and never used, variables that are used that were never defined, things that are imported and never used, just common mistakes and things like that. And so I ran into a problem with the project that I was working on that we inherited a code base from some contractors, and they had defined all these functions and all these objects and they never used them anywhere. And so a lot of my day-to-day was encounter a function that's defined, and then grep over the code base to find if anybody ever called it anywhere. And so after doing this a couple of times, I was like, can I use regular expressions in order to solve the problem? And then you get into, well, you're writing some kind of you're basically writing a tokenizer within Python, and it turns out that Python did that already. And so using the AST module, you can treat Python programs in this sort of like node-oriented way. Or you can treat the individual tokens as nodes within an abstract syntax tree. And another project that does this to a lot of success is MacroPy, which really is a project that seems like somebody was really interested in Lisp, and then they were forced to write Python, and so they re-implemented macros in Python. So I don't really know if it's a great idea for you to use MacroPy within production, but it's a really, really interesting project to dig into. Like, how would you begin to sort of, in a meta way, evaluate these Python programs and then rewrite abstract syntax trees? So I keep on using the expression abstract syntax trees. Does everybody here kind of know what that is? And to be completely honest, my computer science background's not super strong, so I'm going to use hand-wavy things about any theoretical implementations of abstract syntax trees. But basically, the idea is, if I have some program like this greatest common denominator function, and there is, I'm going to attempt to use my cursor here. There's a while loop, then there's a conditional, and then there's some variable assignment. There's the other side of the conditional, which has a different assignment, and then there's a return statement. Well, I could break this down into this tree-like structure where I have my while, and then I have a comparison, then I have branches, and there are sort of different pieces of those branches. And so instead of having this like text-oriented thing, Python actually looks this way because it has white space. But sort of the idea of how can I take these individual pieces of the program and look at them as if they're a tree. And Python gives us these really awesome tools to do that. So the easy ones, you can dive into how the interpreter is actually implemented, but there's some convenience objects that they also provide for you in the form of node visitor and node transformer. So node visitor gives you the ability, sort of if you start at the top of a tree for a program and you want to just walk through all of it, similar to the way that you would use like OS walk in order to walk through a directory structure. Now I want to walk through every single branch within this abstract syntax tree within Python. They give you a couple of different methods that you have to override. So node visitor is meant to sort of be the abstract base class that you override methods on. So you can override either generic visit or visit, and then it's an underscore, and it's the class name of the kind of node. So if you wanted to override like visit function definition or visit function invocation and all the sort of different classes of token. Yeah?
Is that implemented as a straight B tree?
Sorry?
Is that implemented as a straight B tree?
I honestly don't know.
Okay.
Sorry, the question was, is that implemented as a straight B tree? And I don't know the answer to that. I would be really interested to find out if anybody has Google or access to code. And in fact, like I'm not an expert on this. It was just something that I kind of stumbled through and wanted to share. So if anybody can increase my knowledge on the subject as a part of this talk, that would actually be really cool. So the node visitor class very specifically doesn't modify the AST in any way. All it's going to do is allow you to sort of traverse through this tree, and then everything that you encounter you can keep a record of however you want, or otherwise sort of do any kind of analysis. So I've got a really simple version of that, which is just this simple visitor, which is going to subclass node visitor, and then we're going to override generic visit. We're going to receive self, node, args, and kwargs. And then print the node, and then call super on it. So if I don't call super, then I would stop sort of as I'm going through the tree. I wouldn't traverse any further past this node. So you have to always call super in order to make sure that you continue sort of that traversal. So let's make some code to play with. I'm going to define a really simple function. I'm going to use a really unique name, foo, which no code example has ever done before. We're going to take b, we're going to make b 2 plus 2, again, breaking the sound barrier here, and then we're going to print a. So now with the power of Python introspection, I can actually get the source code of a defined function. So inspect.getSource, and I will pass it foo, and that's going to give me back a string representation of that function. And then I can say, I'm going to instantiate an instance of my simple visitor class. AST.parse is what's actually going to take text files and turn them back into an AST. And I'm going to inspect that function foo in order to get the text representation of the function foo. So now I have example AST. An AST comes with a convenience method dump, which basically will just give you, hey, here's everything that's in this AST. And you can see here that I have module, and then I have body. I have a function def, it has names and arguments and things like that. And this actually, I mean, really was just the cool kind of moment for me whenever I started playing with it. I was like, oh man, I can like get every individual piece of this and then treat it as if it's another object. Yes?
So does that inspect actually set where you're starting at in the tree when you read that in?
Does the inspect start where, sorry, say that again?
You've got a tree.
Mm-hmm.
It's like all your code that's been broken out into the abstract syntax. You've got that inspect in there. Is that setting what node that starts at?
So what the inspect is doing is it's taking the function that I defined and allowing me to get that back as text. So if I wanted to get the abstract syntax tree of an entire file, I could just pass the text from a file into it. In this case, I was just showing that I can define a function and get the text back from that function. So it's only going to give me it's going to give me the AST at the sort of highest level that I start at. So if I passed a whole file in, I would get that. Yes.
So it looks like in the previous slide,
Mm-hmm.
pass it in the top, and then that's why you call it super, so it continues traversing the tree. Right? So
Yes.
you started basically where you want. And
Right.
As you have super, it follows the full tree.
Okay, and yeah, so what he's saying is basically, since it's going to visit, sort of, I'm going to go back to my other slide of an actual tree.
You see what I'm trying to get? It's like, how are we really like parsing through it to walk it?
Sure. So you just have AST as an object, and then you can walk through it node by node. So if I wanted to pass in a string representation of just like a conditional statement, for example, not even a function, then I could get the abstract syntax tree of that back. But wherever I start, that's going to be the sort of the root of the tree. I don't really know if I'm explaining that better. If anybody else in the room feels like they could give a better explanation, again, we're all learning and loving and all that great stuff together. Yeah.
The confusion is thinking that the AST is not actually returning the object of the execution of the program that he's running. It's being passed a string and it's evaluating that and building the AST of just that string. Just the string. Not of the actual execution itself.
Yeah, exactly. So none of this is actually being executed. This is more of like a static analysis kind of step. So like if I have some textual representation of a program, how can I then get back to like a tree representation of the program? Where was I?
Sorry, could you go back one slide for just a second?
Sure. So I'm just defining the function foo, and then below that I'm showing you can use Python's introspection in order to get the code back of what that function definition was.
And then in the following slide, I guess I'm just not seeing you create a simple visitor.
Mm-hmm.
You're creating an abstract abstract syntax tree, but I don't see how you combine.
Sorry. Yeah. Grand reveal.
That was the piece I missed.
Ta-da! Okay. Yeah, and all I was really showing was, so the AST module here provides this convenience method of dump, which is just, give me everything that you have within this variable so that I can see it. And a lot of times, like whenever you're messing with things like that, it's a really convenient thing because you want to see like what is sort of within this subtree, and you can also start treating things as subtrees. So like earlier I said, if I took an entire file, I would get the AST of that file. Well, I can take any of those subtrees off. So if I just wanted the subtree of a function definition, I could do that. If I just wanted the subtree of an object definition, I could sort of begin to pass those objects around themselves as well. And all this very simple visitor was doing was just taking one and printing it out as it would traverse it. And so back on my other slide, and so I'm going to go back and forth a lot. I defined this generic visit. I'm printing the node as I encounter it, and then I'm calling super on it so that I continue to traverse through it. And then you can see when I do that, I just get all of these printed out. Yeah?
I don't know if it completely answers your question, but based on the way that the order in which those are printed out, it looks like, well, one, it's an infix notation for the tree, because there's an add between two nodes, but also it looks like there's probably 3 children that have been up, so it's probably not a tree.
Yeah, you get, right, it's more like B++ kind of.
I mean, it doesn't really matter quite how it's probably.
I don't even know that I can repeat that. So he's in the back of the room just like, just keep on saying. So that was a really, really simple example, and it is basically just the equivalent of re-implementing dump in some way. Let's do something that might be a little bit more interesting, and this is really, I'm going to sort of walk through the problem that I encountered with trying to find functions that are defined but never called. And there's a really simple piece of code that answers that question. So a more complicated example. How well does this show up on the projector? Because that's really going to... Okay. So this is my class usage analyzer. And again, I'm going to inherit from node visitor, which is provided for us from the AST module in Python. As a part of my initialization, I'm going to set 2 variables called function names and defined function names, and those are just going to be sets. And I'm going to call super on that, like you would with any constructor. And now I'm able to subclass these visit underscore, and this is the type of node that you're encountering. So there's an import from, function definition, call, and if I go back to the previous slide, you can see assign, name, store, binop, num, add, print. Basically every single kind of built-in within Python has its own AST node type. And so anytime that I encounter those, all I have to do is override this visit underscore and then whatever type that is. Honestly, the documentation is really, really lacking on this one. What I ended up having to do to figure this out was I overrode get adder and just watched as all the messages kind of went by on that class in order to figure this out. And that's really the only documentation that I know to exist. There may be something else somewhere in the bowels of Python, but I haven't really found a great piece of documentation for that. And in this particular example, I wanted to know what things are defined and never called. So if I have visit function def, then I would just, as soon as I encounter a function definition, self.define function name add, and then I have node.name, which is just the name of that particular thing. And then I call generic visit so that I make sure that I continue to traverse through the tree. Up here, every single time that something is called, there's a little bit different way that the nodes appear if it's a method on a class versus just a typical function invocation. So for here, if it has if an ID, then I'm going to get the name as node.function.id. Otherwise, I'm going to get it as node.function.adder. And that basically, again, just allows me to say, is it an invocation on a class or is it just a typical function invocation? And then I'm going to add that to self.calledFunction names. Down here, whenever I then want to say I've gone through all these different ASTs, and I want to find everything that's defined and everything that's been called. I just have two sets, so I just do the difference of those sets. And that's going to be the things that were defined and never called. So again, just like super simple, and it was something that I thought was going to be a really complicated problem if I tried to do it with regular expressions, and Python provides a module that I don't have to. Yeah?
So when you had this, did you write like a little test code example to assign a function to a variable name and then later call that variable name?
I didn't, so the question was, did I write a piece of test code to assign a function to a variable name?
Like, is this finding all the call sites, or is it finding like?
So it's like, imagine that you had a file that's just full of like def foo, def bar, def baz, def, like all of those different function names, and then you want to know, are those functions ever called anywhere within a directory?
Right, but will they be called directly? But if you assign that function to a variable name and then invoke the variable name?
You're running into the halting problem at that point, because then you would be, so like as a static,
Statically detects. I don't know if this actually did detect it automatically, or if that.
no, you're just going to look, basically a slightly better version than doing in regex is just some way to sort of like walk through and say, okay, here are all the places that it's called, here are all the places that things are defined. Yeah?
So if you modified there's an assignment object, so you could overload that, like you overload the call object.
Absolutely, and there's tons of things that you could do. This is just a really simple example.
No, I think it just address the problem.
Yeah, absolutely.
And really, there's nothing else. Is there any other?
So if you overrode getAtter anywhere and you were doing kind of like string manipulation in order to find things that you wanted to call, yeah,
Yeah, but practically speaking.
sure, absolutely. I think there's tons of things, and practicality and theory, kind of the intersection there, are interesting as well.
Have to have just a general way of handling aliasing.
Right.
Cool. So the other thing that you can do is you can transform stuff. So we sort of mentioned earlier that MacroPy exists, and I'm going to give a really simple version of how you might modify a piece of code, and then I'm going to warn you that you shouldn't use my example. You should go look at MacroPy because he's thought about it a lot more than I have. So instead of importing node visitor, we have node transformer, and it functions very similarly to the way that node visitor does, except the difference is if I return a new subtree of an AST, that's going to be what's used instead of just visiting. I'm going to be able to actually make transformations of subtrees. So let's look at that. One idea that I've had a lot of times, instead of having to jump into a debugger, it'd be really interesting to sort of watch code as it goes by, like what's actually taking place at every single sort of evaluation of a conditional or every single iteration of a loop. And so the idea with this object is, could I write something that would modify the AST in such a way that it would just inject print statements in between every single line of this is what's going on while a piece of code is going by. So return a new, take an AST, modify it in such a way that it prints everything that's happening, and then whenever that code is evaluated at a future time, you would then be able to sort of watch it print, hey, this is what I'm doing. All this one is going to do is print, I'm in your codes at every single line, but again, it's sort of an example of how you might be able to start tackling a problem like that. So I have generic visit overwritten, and now it's going to, instead of returning just the node that I received, I'm going to return a module node that then has a print node contained within it. Destination is equal to none, and then its values are another string node, which is I'm in your code. And again, from the AST module, you can import all of these different objects. So anything that's built into Python, you would then be able to sort of inject that. So I'm going to instantiate an instance of the what's happening object, and then again using inspect.getSource on my foo function from way back in the other slides, I'm then going to return a new AST, and you can sort of see that happen here. Whenever I call ast.dump, there's now a print in front of the other definition of those things. So you would then, after you have an AST, you can turn it back into bytecode, and then you can assign that back to a variable. So yeah, you can modify, take something that's living, modify it, and then return it back. And again, there's some details there that I'm really glossing over. And if you think that's interesting, go check out MacroPy. Cool. questions on how any of this works that I may or may not be able to answer, or that we as a group that we're loving and learning and moving together into the future together that we might be able to figure out. Sure.
I'll tell you what I like about this. I don't know if anybody's familiar, like in the Java world with Sonar Source, but this is like a really good way to start to look at what kind of test coverage you actually have across your code base. If you start looking at your unit test as the syntax tree, and then you start looking at the code that they're calling like that and doing comparisons, you get that kind of how much test coverage do I have within my code base.
There's a tool called Coverage PY that does exactly this.
There's another, and I'm going to completely blank on what it's called. Basically, testing your tests. So if I wanted to take a piece of code that was under a unit test and then modify, reverse, say, like some kind of operator, instead of something being greater than, have it be less than. The idea behind unit testing is that should then fail the test. And so there's sort of an approach to testing where you would then go through and sort of just swap things and then run that new modified piece of code and then verify whether or not your unit tests passed or failed. And that's a way you can sort of evaluate how well your unit tests are written. And there's a name for that approach to testing that I'm completely... Yeah.
But is there a Python library that does that?
There is one, I think it's called Mutant. I think there's just tons of really cool stuff you can do whenever you start treating Python as something that you can modify sort of as it's going past. I wish that the documentation was a little bit better. Given my copious amounts of free time, I'd love to write some more. Yeah?
How well did that project that you were working on go after you figured this out?
It basically allowed us to go in and just nuke all of the dead code.
How much did you do? I'm assuming it's like an average project.
This was not an average project. It was pretty bad. I think we ended up deleting like 150 or like 200 different like functions and objects. One of the things, it was a Django project, and again you get into that like meta problem where like Django is going to use some things that aren't actually defined within the scope of the project. And that code's actually available on my GitHub, by the way. It's I released it as a project called Python Morgue because it found the dead code and things. And you can go check that out. And it's just basically the class that I gave as an example in this talk. Yeah?
Might be a good idea, but is it possible to use this to generate unit tests?
To generate unit test cases. I guess it would be. I don't know what the validity of that would be. Does anybody have an idea, like what it would be like if you attempted to generate a unit just based upon like, is this doing the exact thing that I expect it to do? Chris?
You would, at doing that, you would get maybe some value from like, at a regression standpoint, like, but you don't get any of the design value of it that you get when you actually do CUD. And it's plausible that like, your actual regression is so tightly coupled to the implementation that it doesn't matter. So it's probably, it probably has very, 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 very much value.
Yeah, you're kind of testing the interpreter at that point, right? Yeah.
I'm not sure if it would actually generate a unit test, but it would be great for building boilerplate. So you define a class, and then all of a sudden you have a unit underscore test class, and there's boilerplate definitions. So you just add
Yeah, that would be fantastic. Like I said, I think there's a ton of stuff that you can do whenever you stop sort of thinking of Python as like a text representation and start thinking of the individual pieces that it's actually defining. Yes?
One thing I've seen this kind of stuff used for is for testing and evaluating TED and unit tests. What they do is they mutate the syntax tree and then see whether or not that change is detected by your unit test. And if it doesn't, that means there are probably other test cases and scenarios you should be thinking about.
Yeah, and I don't, mutation testing that we were talking about, I don't know, or like I know it can take a really long time to do that because the set of possible like mutations is so large that then you'd have to run your entire unit test suite against every single possible mutation in order to...
It doesn't need to do all of them. It does things like if you've got a conditional, if x is less than or equal to y, it changes it to if x is less than y, and see. Do you have a test that fails when they did that? If not, why is it the way it is?
Yeah, I think that there's some cool things there. Another thing, I have kind of an interest in just different functional programming ideas, and I think that there is a way that you could, given a function that's defined in an outside library, look, does it make any system calls at any level in the tree? And if it doesn't make any system calls, then you can assume that it has referential integrity, and you could do something like a memoization of an outside function, based upon, is it just reacting to the inputs that I give it, or does it have side effects, and sort of this notion of like using ASTs for side effect detection. Yes?
Protecting dependencies.
Yeah, absolutely. I mean, and another, even things like, could you create a search tool within Python that's more context aware? So instead of just using grep, like if you wanted to parse through an entire directory full of code and then use some sort of like SQL-like search against definitions of, give me modules where this is defined or this is used and things like that. There are just a lot of different things that you can use the AST module for, and I think it's a module that nobody really digs into, and that maybe because of the documentation. Yeah?
So there is this PyScope tool that I think uses the AST to generate the C-scope ED that you can use to scan your Python project for like function calls and function definitions.
Okay.
Is that called?
PyScope.
It's, I see.
Yeah. It's using C-scope to,
Cool. Well, really the reason for the talk is you guys need to go out and write all this stuff so that I can use it. Thanks, everybody. Anything else that you guys want to talk about? Awesome. Thank you.